This is the first video in a chapter about atoms, molecules, and ions. We're going to talk about atoms and what they're made of, and then we'll talk about how atoms fit together to form molecules and compounds. So that we'll start with the evolution of atomic theory, or if that doesn't sound interesting to you, Harry Potter and the evolution of atomic theory. It's going to be a series of stories about how our view of the atom developed through history, with a couple of important experiments that led us to discover atoms, electrons, and protons and neutrons. So we'll start with atoms because that's the biggest of the group. So in the previous chapter, we talked about the scientific method, the main tool that scientists use to discover things. So we'll start there. Scientists use the scientific method to make and test hypotheses about how the world works. And we're going to turn the clock back a couple of centuries, and we're going to picture we are scientists back in this time and think about what sorts of questions are important, what we'd want to use the scientific method to answer. So the question on everyone's minds is this: what are things made of? Specifically, what is matter made of? We've all wondered. And at one point in time, there wasn't an answer yet. And someone had to dream up what matter might look like if you were able to zoom in really, really close. So the first folks to comment on what they thought matter was made of were way back 5th century BC Greek philosophers as a group. So these folks were not quite at the experimentation level of the scientific method. They were just at the make observation form hypothesis phase. So their hypothesis was that all matter is composed of small indivisible particles. And that if you looked closer and closer and you broke up a compound into something smaller and smaller, at some point you would reach the smallest unit and it could not be broken any further. And they called these atoms. And we still call them that today, even though they made this hypothesis that was a total and complete guess with no proof. It was close enough to the truth that we continued to call them atoms. So that was sort of like the general idea for a great number of years. The first actual experiment to start to prove that that might be true wasn't until 1789. And that was by a Frenchman by the name of Lavoisier. Based on his experiments, Lavoisier studied mass and how the mass changed during a chemical reaction. He would do experiments inside of sealed containers, as well as they could do at the time, and watch how the total mass changed. So he observed the total mass of all components in the reaction, solids, gases, liquids, visible or invisible, before and after a reaction. Remains a constant. And this is officially known as the law of conservation of mass. This may take a minute to think about, but you should be able to prove to yourself that it's true. If you were to put a candle inside of a sealed jar and to light it and to burn it and to keep it on a scale the whole time, the mass should be the same before and after, as long as you include the gas products that were made. And so we can make a jump from this. So if the total mass remains the same and all matter is made of atoms, then we can conclude the number of atoms of each element should also remain the same, because they didn't go anywhere. So they can't have changed. They just rearrange themselves. So let's draw that out. So if we had some compound, we'll say it has 2 red atoms in it, and we had some other compound that had 2 blue atoms. If we reacted those together, we know that however they end up at the end, there still should be 2 red atoms and 2 blue atoms at the end. So maybe we made molecules that looked like this. Maybe we changed the partners. Or maybe we didn't. Maybe nothing happened. We can't predict what happened, but what we can predict is that the number of blue atoms and the number of red atoms before the reaction and after the reaction should remain the same because of the law of conservation of mass. So that's cool and useful, and it supports the idea that matter is made up of atoms, these small indivisible units. The next chapter in the story is about a guy named Proust. And based on Proust's research, he said that compounds had a specific ratio of mass that didn't change. So the ratio of the mass of each element in a compound is a constant. And this one is formally called law of constant composition. So let's talk about a compound that you probably are familiar with, and that's water. You know, water has a formula of H2O from your previous chemistry experience, and we can draw it as 2 little hydrogen atoms and a big oxygen atom. And so Proust said the ratio of the mass of the different elements remains a constant. So there are 2 elements here, the hydrogens and the oxygen. And so this says that no matter what mass of oxygen we have, the ratio of oxygen to hydrogen is going to be the same. So here we have a ratio of 16:2, the ratio is 8. So if we had 32 grams of oxygen that were detected, then there must be 4 grams of hydrogen, so that that ratio 32/4 equals 8. Or if we have 8 grams of oxygen, then we must have 1 gram of hydrogen. Oops. So the ratio of the masses of the different elements, no matter how much of each there is, the ratio is always a constant for constant composition. Okay, so there were some early ideas about what an atom might look like, and we're going to move on to the next very important player in the process, and his name was Dalton. And Dalton was a school teacher who was very well read in the chemical literature, and he didn't do any unique experiments himself, but he put together the ideas that he read in the literature and synthesized them into an atomic theory that is mostly true up to this point. So you can see that I've cheated and I've written the parts of his theory ahead of time. So please pause the video and write them down, and then we will talk about it. Okay, I'm going to assume you have these written down at this point. So Dalton's atomic theory has 5 important parts. The first part says matter is composed of tiny particles called atoms. So this is based on the hypothesis from the Greek philosophers, and it's still true. So if you take something and you break it and you break it and you break it into a smaller and smaller and smaller piece, eventually you will reach a smallest size particle. And when you reach the smallest size, that's going to be called an atom. The second facet of Dalton's atomic theory is that each element consists of one unique type of atom, which has a unique mass. So an element, that's one element from the periodic table. Every different element has one unique type of atom with a unique mass. So you might have an element with one mass, or you might have a carbon atom with a different mass. You might have an oxygen atom that has a different mass. You might have silicon that has a different mass. By the way, this is definitely not what atoms look like. But what this says is that anytime you find a carbon atom, every carbon atom is going to have the same mass and it's going to have the same properties. And I think that's actually our next facet of the atomic theory. The chemical properties of an atom of a particular element are unique. So every time you have a carbon atom, that carbon atom is always going to be reacting with a certain kind of molecule, not reacting with a certain kind of molecule, melting at a certain temperature, freezing at a certain temperature, dissolving in certain substances. The chemical properties of a particular element will always be the same. That's how we identify what element it is, by the chemical properties. The fourth facet of the atomic theory, a compound, that's a word we learned in our vocab list. A compound consists of atoms of two or more elements, and they're combined in small whole number ratios. This ratio is constant for a particular compound. So like we looked at the formula for water. The formula for water is H2O, and this is a compound because it has two or more elements. This is an element, hydrogen, and this is an element, oxygen. There are two elements, and so this is a molecule of a compound. And the elements are combined in a small whole number ratio. So there are two hydrogen atoms, and there's one oxygen atom. So the ratio here of hydrogen to oxygen is 2:1. So every time you have a compound, the elements are going to be combined in small whole number ratios, and it's always going to be true. In order for this molecule to be considered water, the ratio has to be 2:1. If the molecular ratio was different, if the ratio of hydrogen to oxygen was 1:1, then this wouldn't be considered water anymore. This one with a 2:1 ratio would be water, and this one is different. This one is hydrogen peroxide. So we've seen that an element is defined by the mass of an atom and the chemical properties of those atoms. And a compound, which contains multiple elements, is defined by the small whole number ratio of those elements. And finally, atoms are not created or destroyed during a chemical reaction. Rather, they are rearranged to give new compounds with new properties. So this is like the example that we drew on the previous page. If you have some sort of a compound and you mix it with another compound and they have a chemical reaction, those atoms don't go away. They are simply rearranged in a different order than they were before. And so the compound may look different. It may have different chemical properties, but the total mass will remain the same, and the total number of atoms of each type will remain the same. There are still two red atoms and two blue atoms before and after the reaction happens. So in the next few videos, we're going to be talking about what the current view of an atom looked like. So we're going to start a log of what we think the atom looks like and update it as we move through time. So the first person to hypothesize what an atom looked like was Dalton. So let's add Dalton at the beginning, and we're going to leave a whole page for this, and I suggest you do so as well. So what does an atom look like as of 1807? Dalton was the first widely accepted person to comment on what an atom looked like with his atomic theory. And Dalton said an atom was a small, indivisible particle, and you could identify what element that atom was by how much its mass was. So if you had two atoms and they had the same mass, we'll talk about these later. This is an atomic mass unit, a measure of mass. If two atoms have the same mass, then they must be the same element. And if we have two atoms and they have different masses, so let's say one of them is 3 and one of them is 4 atomic mass units, then we're going to say these are fundamentally different elements. So we are at 1807. The atom is a small indivisible object that is defined by how much its mass is and what it reacts with. In the next video, we'll move on to the next century and talk about what else we've learned about what an atom looks like on the inside.